Hello everyone. In this video we will continue to examine topic 7.1, discrete energy and radioactivity, and in particular we will begin to understand discrete energy and discrete energy levels. So in the last video we considered electromagnetic, or the general electromagnetic spectrum, that is sort of the conceptual space of all possible electromagnetic waves as organized by wavelength or frequency or energy. And our definition of a spectrum here is a distribution, in this case, of electromagnetic radiation arranged by the wavelength or the frequency. So we have this general electromagnetic spectrum. Those are all possible electromagnetic waves, but we can also produce real physical spectra. Why or how? Well, we can take sources of light that have many different wavelengths of light within them, and using a number of techniques, we can distribute them spatially by wavelength. So consider for a second an incandescent light bulb. This is a light bulb that is producing incandescent white light of a standard variety. This produces what is known as a continuous spectrum. So what do I mean by that? Well, if you take this light and you shine it through a prism or a diffraction grating, both of which we discussed in topic 4, that will spread the light out into its different wavelengths. Okay, why? Well, in the case of a prism, it's because the refractive index of the prism depends very slightly upon wavelength, and so a prism will distribute those wavelengths into a spectrum. And a diffraction grating is also sensitive to the wavelength. So we studied that in topic 9 for HL. Notice that prisms are made of glass or some kind of clear lens, and so actually, as it turns out, the vast majority of spectrum-producing items use a diffraction grating, which is a little easier to use in practice, if not to manufacture. Just as a side note. So you take all the light coming from the incandescent white light and you spread it out into what most ordinary human beings would call a rainbow. And it's a full rainbow if you have a continuous spectrum. Okay, so there are actually different kinds of continuous spectrum, but the idea is there is at least some light at the different wavelengths. That is, there is some light at red wavelengths, some light at orange and yellow and green and blue, and so there are no gaps, and there are no particularly bright spots. Well, I have to be a little bit careful about how I say that, but for example, there's not a random spot in the red here that is particularly brighter than the areas around it. This is known as a continuous spectrum. In later units, we will discuss the exact nature of this distribution. As it turns out, it's not exactly what you would think it would be. I think most people would sort of intuit that you would have equal amounts of brightness for red wavelengths and purple wavelengths and green wavelengths, but as it turns out, it's not quite true, and in fact, there's significant temperature dependence on which wavelengths are brightest in what is known as a black body spectrum, and we'll get to that in due time. But it's important to note that even a black body spectrum, as shown here, is a graph where you have a certain amount of intensity versus the wavelength, and you can see that for a particular temperature, you get some wavelengths over here and some wavelengths over here and some over here. That will give you a rainbow, and that is what is known as a continuous spectrum. Okay, so given that, as it turns out, there are ways of producing light, okay, that give us non-continuous spectra. And we'll tackle the first kinds of those first. So if you take a thin gas, that is a gas that is not very dense, think of helium gas or neon, there are a whole bunch of different kinds of gas, and you apply a very, very high potential to it. So in particular, you apply a high potential difference using a set of parallel plates. This creates an incredibly strong electric field, and if you crank it up to in the range of thousands of volts, you will actually begin to break down the atoms in a process we will describe later, and you will produce light. So you apply a very high potential to a thin gas, and you get light that looks like this. When you think of in ordinary life, those things we call neon lights or mercury lights, this is exactly what is going on. So a very high potential difference is being applied to a thin gas, and that thin gas is producing light. It turns out that if you take that light and run it through a prism or a diffraction grating, you don't get a clean rainbow. In fact, you discover that the light that you get is split up, and you only have very particular wavelengths of light inside that source. So, as it turns out, this particular picture is from hydrogen, and if you apply a very high potential difference to hydrogen, you get this sort of generally pink light. But if you run that light through a prism or a diffraction grating to split it up by wavelengths, you discover that there are actually exactly 4 colors of light. There are exactly 4 wavelengths of light in that original spectrum. There's one at red, one at sort of usually represented as turquoise but bluish, and then 2 sort of fainter purple ones. Okay, that is represented here in sort of a visual spectrum. But you can also graph it, and we will discuss sort of graphed spectra quite a bit, where this red light is quite bright, and it corresponds to this wavelength here in the graph. So if I zoom into the graph a little bit, you can see that this wavelength, these are higher wavelengths, and so these are red, these are lower wavelengths, and so these are violet, and you can see that there is a peak that corresponds to this red peak right here. The next one over is that blue or turquoise peak. You have a purple peak next to that, and over here you have a very faint purple peak. And these are the ones that are visibly observable. So you can run this through a diffraction grating and see for yourself these particular peaks. And we'll discuss more about why they are where they are moving forward. But for now, we're left with this sort of interesting mystery, which is if you run a high potential difference across a thin gas and break down the light, you are left with what is known as discrete wavelengths in that light.